This technical presentation will be given by senior consultant Abdulrahman Al-Khowaiter. Abdulrahman Al-Khowaiter works for Saudi Aramco with over 35 years of experience. He is a down-to-earth engineer who would like to solve problems across the board of mechanical engineering. He's specialized in rotating equipment, compressors, steam turbines, a pump, you name it. And also he has a very track record of giving technical presentations and technical courses in fault analysis and failure analysis mode. Please welcome with me Abdulrahman Al-Khowaiter with his presentation, Machinery Switchover Frequency Optimization and Methodology for Plant Machinery.
Good morning, gentlemen, ladies and gentlemen. Okay, I'll be presenting this through my presentation will be presented through a PDF format because the PDF captures a lot of information that we cannot put in a PowerPoint. And you'll be given a copy, of course, whenever you request it from the course organizers after the conference or now you can request it. It's a critical subject, which is rotating equipment switchover frequency, how to maximize how to improve the time intervals that are selected for the rotating equipment switchover frequencies. So this is a major issue in all process plants, especially process plants, but industrial plants also frequently have switchover issues, which is when do you need switchover? You need switchover when you are having multiple machinery. If you only have a single line of machinery in a certain process or a certain industry, then obviously there's nothing to switch over. You have that single machine and you're operating with it. But in many industrial situations, you have multiple machines, and then these machines should be switched over due to multiple reasons why we switch over equipment, but they have to be switched over. So, since I started in the industry year 1988, I only had a few, maybe 6 months of actual plant operating experience at that time. Then later in 1994, I spent full-time 4 years at a reliability unit in a very large industrial process plant. And that's when I was faced with the issue of the switchover, and that I didn't feel it was optimized at all. At that time, they were switching over typically once every month. That would be 12 months. For every 12 months, there's one switchover. If you have an A and B machine, you're switching from the A to the B at that 1 month interval. And as you know, and other plants might have had a 2-month switching interval. So 2 months on for the A, and then 2 months on for the B, and then back to the A. But then when you get A, B, and C, more troubles arise because now I have A, B, and C, A, B, C. Yes, if you have A, B, C, you have 2 running. Let's say A and B is running, and the C is the standby machine. So again, you got to switch from the A to the C, and then maybe C back to B. It's a mess. It's a hassle. Okay, let's go on into the issues. Now, industrial plants utilize spared machinery to provide higher plant availability, as machines can fail and standby machinery are critical to the process. Okay, so nobody wants the machines to fail. That's why we're switching over. It means that plants incorporate a scheduled switchover frequency, usually of once monthly period between the operating machines and a standby sister equipment. Some plants even use 2 weeks as a switchover frequency. Others might use 2 months. This report attempts to optimize the switchover period to maximize plant machinery safety, reliability, and reduce operations workloads. The authors worked with over 200 process plants during the past 25 years, and over time recognized that industry in general is not applying reliability-centered maintenance towards switchover practice. Okay? We cannot follow the past blindly without asking ourselves, is the past correct or not? Is it optimized? Okay? Maybe not. If you're in a transport company, you're using 10-ton trucks, okay, and you find out 90% of your packages and your total weight that you're carrying is only 5 tons. Well, you're not optimized at all. You could be buying 5-ton trucks, and they'll do an excellent job, and you only need the 10-ton trucks for 10% of the time. So all that weight going along the highway, extra fuel, extra cost, first cost, was wasted. Nobody optimized it. So same now with the switchover frequency of machinery, okay? So, why do we want to optimize? We want to prolong machinery life and mean time between failure, reduce emergency work activities, increase machinery plant safety, minimize operating expenses, minimize machinery components, corrosion, crystallization, eliminate rotor sagging and vibration problems, establish true hot standby capability. What is hot standby capability? Okay, you have the A and the B machine. You're running on the A pump, for example. It's a critical process pump. Let's say it's a hot oil pump, and it's the only one operating, and the process is relying on it. And now, you thought that the B machine is my standby, and it's ready to go. But when you had to switch over, the A shut down for some reason. It wasn't a planned shutdown, but it was some failure occurred, mechanical seal or something like that. And then you tried to start the B, it didn't start up. What happens to your process? Now your process shut down, major losses, okay? So the B then was not really active and ready to go for the hot standby. So it failed, the B machine. So now you're stuck two failed machines. The B didn't start, the A is failed by itself, maybe mechanical or electrical failure. Okay, so these are many benefits, obviously, and everybody would like to have these benefits in their plant. Okay, time-dependent issues involved in setting switchover frequencies. So what are the time-dependent issues? Machinery shafts and rotors experience some deflection due to gravity weight. So shafts, if they're sitting there in a pump or in a gas compressor, in a steam turbine, maybe large gearbox possibly also, okay? Whatever the machine with, they have long shafts, they can deflect due to gravity weight while they're down. As they're shut down, they're staying 1 month, 2 months, 6 months, shutting down 1 year. There's a gravity deflection that occurs. And it causes you could call it temporary bend. It's going to be there when you start up. Later it will go away, but it can cause trouble as you start it up. It imparts a temporary bend, and it's important particularly for large machines of maybe 500 or 1,000 kilowatt and above. Doesn't happen very much on the smaller machines. They're too small and light. But the bigger machines, they do have the problem. Okay. So, we mentioned sagging of rotors. Next one, bearing housing component corrosion. This occurs to machinery such as pumps, compressors, gearboxes, motors, all machinery. Their bearings, depending on design, including the shaft sealing areas, will be affected by air, humidity in the air. It's always there. And if they're outdoors, and there's also salt particles that are in the sand, that light dust particles in the air, they carry salt with them. Or if you're near an ocean environment, then you have salt in the air all the time. All of these cause corrosion because most of the bearings are typically made of steels. Let's say ball bearings, roller bearings. Sleeve bearings have a tin babbitt, so you can say the tin babbitt is safe, but the shaft itself is made of steel, usually steel alloy. So the bearing is safe if it's a sleeve type, but the shaft can corrode at the bearing area if there was no oil. If the oil had dried away and you left the machine several months. So, while ball bearings are much more sensitive, roller and ball bearings. So that means to protect these bearings, or the shaft itself, they should get an oil film once a month. This is an optimum. Obviously, if you could do it every day, oh yeah, it's fantastic, but that costs you money, it costs you time. So what is the real need? 1 month interval. You don't want to go to 2 months because the oil film is the one that's protecting them from corrosion, extends the life, and all this business. In addition, gearbox teeth need oil once a month, okay? They don't want to be swimming in it 24 hours a day. If they could, okay, great, but once a month is nice, enough. Centrifugal compressors, they have dry gas seals, or usually these components don't have a corrosion issue. However, you need to maintain the nitrogen purge on them. That's easily done. So nitrogen purge could be done continuously to preserve the machine from corrosion as the machine is down, because it already has a nitrogen connection to the dry gas seals. So that's just to remind you of this is something to do on all your gas compressors, for example. Make sure the controls are keeping the nitrogen to the dry gas seals. If it's going to tertiary or going tertiary and primary, between the primary and secondary, keep that nitrogen on while the machine is down. Okay, number 4, pump mechanical seals. Mechanical seals need to have the sleeve and faces rotated with fluid to reduce fouling buildup, adhesion, and lubricate connecting parts. So what we need, when I said fouling buildup, this is discussing really like crystallization of salts and things like that happen to be in the fluid when it was running. So once it's down, that buildup of those salts can stay there, and then you get adhesion, and we also want. They need to have the sleeve and faces rotated. What for? Why do we want them rotated? To eliminate the fouling buildup, adhesion, where the two surfaces stick together and stay stuck, and lubricate the contacting parts. The adhesion force during startup will cause face and spring failures. Okay. So that's another reason. That's number 4. Number 5, internal corrosion or salt fouling. So now, let's say inside it's a pump or whatever the machine is. In some process machine applications, they may have internal corrosion due to air or gases trapped in the casing on long shutdowns. Includes reciprocating engines and gearboxes whose gears require lubrication of all surfaces. Okay? Number 6, rolling element bearing static load degradation. As the machine is sitting there, it gets degraded from, as we discussed before, oxygen in the air plus salts. And without an oil film, they get corroded. But here I also mentioned that on modern bearings, I wouldn't worry too much about microscopic deformation of the dead weight of the rotor when machine is off, because machines have much better designed bearings now. They're more superior bearings than they were 40, 50 years ago. And their loads are lower. In the old days, they made big mistakes by having excessive loading, static load of the shaft or rotor on top of the bearing, and the balls would be having very high Hertzian stresses, the ball or the rollers. Nowadays, people are putting on larger, heavier duty bearings. They're forced to, from industry requirement for higher reliability. So the bearings actually have less loading per unit area. I'm talking rolling element bearings. And they're much harder than they used to be. So in the past, they used to be maybe Rockwell C, 40, 50 in the past, 55. Now they're 60, 62, 64, Rockwell C. So I wouldn't worry too much about the static load degradation issue on rolling element bearings. Okay, another issue, failure to start on demand. This is the number 7 reason why we want to have some kind of startups switching over. Okay, these are all the reasons why we want to do some kind of switch over to make sure that the other machine is workable and to protect it from the issues that we discussed. So the plant operation personnel need to test the standby machinery to determine if they have the hot standby capability of being immediately started. Otherwise, it's not ready. So the operators will tell you, hey, your machine is off now, and we might have to switch to it, but we're worried about it. So if you try to keep it there 1 year without opening, without starting it, whatever, and just saying, we designed it well, we're pretty sure it's going to work when you needed it. We're going to leave it off 12 months. Okay, 1 year. We're not going to start it. When you want to switch, you can switch after a year or something. So then when they tested it, they found it didn't switch over. So that means that we need to have to find a way to test, does it have the capability to start or not? So that's another reason why we're doing the switchover. It's really to check, is that machine ready? And can it give us the required, I'm braking sometimes, is it giving us the required service or not? Okay, preventive maintenance. Another reason is we get PMs that we require scheduled shutdowns. So you have the A and B running, or the A, B, and C running, 2, A and B are running, C is off. Okay, the C is easy to do the PM on because it's off. But what about the A and B? They're running. Okay, that means I need to now shut down the A so I can switch to the C, because I already finished the C PM because it was down, just so I can do the PM on the A. And then the same thing happens to the B machine, right? So PM switchovers due to PMs is another reason why we have switchovers. A lot of issues. So what I did in those 8 items is cover every single reason why switchover is needed. Good? I haven't seen a report before this in the industry. If somebody has seen one covering every aspect before, I'd like to see it. But I spent a lot of time doing a comprehensive study of why we need to switch over from all aspects. And I already, of course, we studied what's the industry doing around the world, USA, Middle East, Asia, and I already realized that pretty much everybody's copying from the other without going in depth and seeing, why are we doing it every month? Why are we doing it every 2 months? Nobody's really doing comprehensive because they're afraid. So in the early 90s, when I was young and not having a long-term experience, I realized there must be some issues that I'm not aware of why it was scheduled to be every month, every 2 months. So when you're younger, you can't capture the full picture. You're like a bird flying at low altitude. When you get older, to a young old age like myself, you end up you're a bird higher up in the sky. So you guys think the old guys are just old. No, we actually fly higher than you young guys. All the old men, where are the old men out there in the back conference over there? We fly higher than you are. We can see more than you. And one day you will also. Okay. So, we captured the 8 major reasons, and really there's not many others. Okay. Now, frequent switchover introduces the following negative impacts. Now we said all the reasons why we needed it. What about the negative impact? Now everybody knows these actually already. Number 1, okay, so there's a DIPF curve by reliabilityweb.com. Okay, typical life. Okay, it was designed, and then the green is when you started, you commissioned your plant for this machine, whether it was a pump, a gearbox, a generator unit, could even be a diesel-powered generator unit, could be even the marine. This presentation has really covered every single industry in the world. It could be marine on a ship, marine engines, or marine equipment, or marine generators. Everybody's doing switchovers, gentlemen. Even air conditioning in this HVAC building. They got large centrifugal chillers, typically, and these centrifugal chillers are maybe 2 out of 3. 2 are running, 1 is standby. Everybody has these issues. So you have a proactive domain which you were operating in. Hopefully you had a maintenance system, reliability-centered maintenance, and you're doing well. Look at the green line, nice long life. And then the proactive domain, you're making sure your lubrication is good, and you're adding the proper lubricants. You did a good installation at installation phase. Then you get into a corrective domain where some wear has occurred, and now you have to do some corrections and repairs. Okay, and then you have a reactive phase where you're having to forced to react to the wear-out issues or some other malfunctions caused by operations or other malfunctions. So the frequent switchover, though, can ruin you, can hurt you, because what do we know? As the gentleman from RISS, I think it was, discussed just the past presentation, that PMs introduce infant mortality failures by themselves. Of course, overhauls also do too. So it's not only PMs cause infant mortality failures, but normal overhaul intervals that occur can also cause infant mortality. But we want to minimize PMs, okay? But you're forced to, you have them. So when you had that PM and you shut down the machine for the PM, when you tried to start up the next time, it failed. Why? Because you shut it down anyway, and it might not have been for a PM. Maybe you just shut it down because you want to switch over. But other times you switched over because you had a PM to do, not because you wanted to do the switchover, but it was more the PM forced you. Because it's pretty difficult to do a PM on the machine while the thing is running, right? You're going to put your hands inside it. It's not so easy. So, what are the problems that it causes? On pumps or compressors, we have mechanical seal premature failures. High startup acceleration torque. When you started up your standby machine, or you shut off the A, and you worked on the C, then you came back to start on the A. It was healthy before. You started it, bam, seal leakage. Have you seen this before? Anybody raise their hands? Yes. You wonder why, huh? Here's the reason. Number one, high startup acceleration torque occurs with motor drives, especially motor drives, and causes fatigue failures in the mechanical seal components on pumps. And the mechanical seal vendors never told you this. They never tell you this. It's invisible to the user because you're not living inside the mechanical seal. It's highly detrimental to seal life, including thermal cycling, failure mode, that occurs at every start-shutdown cycle, meaning when you shut it down, there's a thermal cycling downward. And its impact affects liquid seals more than gas seals. For sealless pumps, these are also impacted by thermal cycling mode, okay? But also dry run issues. So why did the mechanical seal fail early? I'm sorry if I keep talking about pumps, but really every machine has similar initial failures that occur. So maybe don't think we're just talking pumps here. We're talking all machinery. But anyway, on the mechanical seal of a pump, as you start up, the torque going through the mechanical seal can be 8 or 10 times what it normally sees at steady state. 8 or 10 times the torque. Why? Because there's friction in the components that make it much harder for the faces to start the rotation effect. And what does it do? Friction causes a reverse torque on the components. So the mechanical seal phases see a reverse torque trying to slow them down. 10 times the normal operating torque of the mechanical seal. At startup only. Because a motor, let's say it's an induction motor, it goes from 0 to normal power in 4 seconds, 5 seconds. That's extremely high acceleration rate. At that acceleration rate, you get opposite friction reduction, trying to reduce this acceleration rate. It's a response, right? When you push something, it pushes back at you. So the mechanical seal faces end up with having fatigue. They can break. The faces can break. The weaker ones, especially the carbon faces, can start to chip exactly at that startup. The springs start to break. All of these problems occur because why? Manufacturers didn't go design it for 10 times normal torque. It's your trouble. That's your problem. Okay, and is it your fault? In a way, you started up too many times. Try not to start them up. Try not to shut them down. So that's what this whole paper is about. Okay, how can I minimize my startups and shutdowns when I have the absolute minimum? So, number 2, internal rotor deflection. Everybody knows this one. The rotors deflect at startup, and then when they deflect, they can contact and cause rubbing inside, whether it's a pump or if it's a compressor or other machinery which have long rotors. Gas turbines, same problem. Gas turbines, same thing. Okay, process machinery, infant mortality. Infant mortality occurs due to operator auxiliaries errors at startup affecting all machinery. It's a common phenomenon in fluid handling equipment and other equipment, but mostly you could say in fluid handling. Why? Because it's relying on a system, whether it's a gas compressor or an air compressor or a pump. In fluid handling, you're relying on a complete system that feeds the pump. So what happens? If the operator missed a valve, let's say a suction valve, and he didn't open it, and you start up the machine, it's going to run dry or some other problem like that, or it can seize and everything. Seize not in the bearings, but seize inside the casing itself, because it didn't get this proper startup. Whose fault is it? It's the operator's fault, yes, human fault. But what if the switchover never happened? Could this fault have happened? No. If you never had the switchover, then there's no operator who's there, sitting there and doing the wrong doing these errors. Okay? Increased safety hazards, fires or destructive failure incidents at faulty startup events. How many times have you heard of failures in your plant or in process plants that occurred at a startup? Can you raise your hands? Yeah, it's a worldwide. Up, they had a fire. When they were starting up the facility, they're starting up this machine. Why? When it was running, it didn't have a fire. It happened during startup because of different problems that occur. Infant mortality. Okay. So thermal cycling causes hot to cold causes fatigue also. We have thermal cycling. And motor starting, electrical installation issues. Excessive startups reduce motor electrical installation life, particularly on larger motors with high amperage during startup and sudden high winding. So this discussion was all the concepts that were causing negative impacts to rotating equipment as a result of the switchover. So first ones, we were saying why we wanted switchover, right? At the beginning, we said, why do we want switchover? Okay, these were the different points. There were 8. Then here, I put in, from a bird's eye view, all the reasons why we don't like switchover. So now we come to, how do we calculate an improved method? Okay, so the main detrimental issues from the above are sudden acceleration torques at startups, rotor high deflections, thermal stresses. Practical conclusion is that 75% of the damage occurs from starting with about 25% impact from shutting down cycles. Okay? Now, how did I reach 75 and 25? By studying all the failures that occur during these switchover periods, what failures they cause. And in other words, what are the failure mechanisms that are affecting the machine upon starting and upon shutting down cycles. Okay? For example, we said that when we shut down the pump, then we restart after several months or something, there's this crystallization on the faces, and the seals, every startup causes high mechanical torque. On a diesel engine, what happens when you're going to start it up? Typically, diesel engines don't have a pre-start pump for the lubricating oil. Let's say you have a generator, 2 megawatt or 3. There's no pre-lubrication pump. So you're starting on the oil that was left in the bearings. And when you first push the button, the bearings only have that oil film. No, that oil pump, is not sending oil to them yet. Only, even though it's shaft-driven, it can't generate enough pressure until after several rotations and several reaching a certain speed and everything. And they'll be, actually, you're running on very low lubrication at that point. And you get wear and tear. And let's say it's a startup diesel. Could be for nuclear power plant. Generation diesel, extremely critical, right? Could be for a ship. Could be your own. So even reciprocating machinery, as you started them, you introduced some damage to them. You could have damage, and you might just have extremely light wear or no wear, depending on how well it's designed and what's the bearing loading, things like that, because they don't come with I was just reading a failure from a ship. They had a 2,000 kilowatt, I think it was a Caterpillar engine-driven generators, and they had switched from the A, and they'd gone to the B. The A was running perfectly. They started the B, bam, and then it seized. Just that startup, okay? It was a switchover event. This is a ship in the U.S. Coast Guard made a report on it. And I looked at the overall, and what did the manufacturer come back and tell them? Say, we recommend you purchase a pre-lubrication pump, electric-powered. The shaft-driven wasn't enough. Actually, there was some other aspects also involved. But that was 50% of the problem, at least, is that they didn't have it. So we said, practical conclusions, that 75% of damage occurs from starting, with about 25% impact from shutting down cycles. Okay, for these reasons, machinery switchovers should be minimized as they're detrimental to reliability. In other words, a standby machine has increased the system availability. So you have an A and B machine, and you're really happy you have two, in case of one fails, or jump to the B, yeah, we started, okay, we're doing good. No problem. We're going to continue on to the Mars mission with Mr. Elon Musk. Okay? Actually, it only has one rocket going, I expect. So it's not two. So there's only an A. There's no B on those rockets. Okay. So the second machine has actually reduced the reliability of the first unit. Isn't that interesting? Has anybody thought of this before? When you bought two machines, you spent double the capital. You bought the A, which was a 10,000 horsepower injection pump or whatever the machine was. Another, which is an identical unit sitting next to it. And you're happy, wow, I have two machines. I'm doing fantastic. Okay, I got plenty of machines now. If the bad operator hit the B, we can always start up the B machine, shut down the A, and we'll start the B, and we'll fire the operator who damaged the A. Good? Yeah. Okay, great. But actually, the B, when you purchased it, reduced the reliability of the A. Why is that? The reason is, obviously, you think it's increased the availability? For sure. If the A was reliable at, let's say, 99%, and both, the A and the B are identical machines, they're both at reliability of 99%. The availability, because you only needed one running, is very high. If one gave you an availability of 99%, and the B, just the A, then I put a second one, the availability is going to go up higher because that 1% of the 365 days of the year might be, let's say, ends up, 4 days out of service, for example. I didn't calculate it exactly. The B now will actually handle those 4 days. If you shut down at that March 12th because of failure, and then you need to start the B, and the B started, then it countered for that loss. So now you have almost 100% availability. Okay? So you're really happy with it. Yes, it gives you availability, but it actually reduces reliability. Because the fact that you have a B machine means you must switch over. And since you're switching over, you introduce all the troubles that we discussed. Well, if you have kept it running, majority of these issues that we raised don't come up. It would have just kept going. Okay. So it reduces the reliability of the A, the B, reduces the reliability of the A, having it, but it increases the availability. Interesting. So here I go through calculations. I don't want to spend too much time on it because I think time is short. How many more minutes do we have? Okay, 5 more minutes. So calculations of start-stop damaging cycles. Here we're trying to optimize how many times and what is the optimum time to do the switchover. I've been talking and talking. Let's get to the numbers. Okay. Calculation of the damaging cycles. For A and B machines, now we're all going to look at B, C, D also, but just simple, A and B. If you have an A machine, if you have a 1 month basis, 1 month switchover, and you have an A, it has 6 starts and 6 shutdowns yearly. A B will have the same, 6 starts and 6 shutdowns yearly. Obviously, you only need one running, but you have to switch. Total harmful cycles is 24 cycles per year. Okay? We said this is the cycles that you're going through. No, because there's 12 shutdown cycles on the A and B and 12 startup cycles on the A and B. Now, what if we change them to I gave a 1 month basis, the first one. Then I tried to show another. We could go to a 2 month, but the 2 month will be similar to the 1 month, not far away. Okay, better, 2 month interval, switch over, but we'll go straight to a 6 month interval. So we don't just keep talking. A and B machines. Now, with the A machine, it will start there on the top. We have a 6 month basis on the same 12 month period, okay? So 6 months is the switchover basis now. One start, one shutdown first 6 months. Then second half of the year, you have a second 6 month shutdown period, one short stop per month. Oh, okay, I'll discuss this. Okay, so one start and one shutdown first 6 months. But on the second half of the year, when A is shut down, you already transferred to B. You're going to now start it up every month, okay? But only a short stop. It's called a short stop. You will start it just to make sure that it works and to lubricate the bearings. And so it's not put online, okay? The machine is not placed online. It's like at no load. It started with no loading, nothing. It's coupled. The motor's coupled to the driver, whatever the machine is. Could be a diesel, could be a pump, could be a motor driving, who knows what. So you start it up, but there's no loading. The minimum load is applied. And if it's a gas turbine, for example, you don't go full load. You don't go to full speed even. You can go half speed, enough. You don't have to fire it up to full temperatures and everything. Because what you're trying to achieve is just a start-stop to lubricate the bearings, lubricate the shafts, and to make sure that the machine can start in all the sequence. The startup sequence command works when you push the button. So it's a test, but also make sure that it lubricates and eliminates any of the issues that we say come from when a machine is sitting down doing nothing. Okay. So these are called short stops per month, once a month you do. So it's not a switchover per month, because the A when it went to the B, I'm not switching over down back to the A again at every cycle, okay? And that explanation is given more over here. Here's the definitions. You can read it on your own. Huh? What's the definition of a short stop, and its benefits or whatever, why we need it. Okay. So if you can understand now, we discussed now 6-month time basis. How many cycles? What the cycles become 7 per machine, it goes 14 cycles per year. Whereas before it was 24 cycles. So we're going to 6 months, we get only 14 cycles for the A and B machine. If I go to 12-month basis, I end up with 13 cycles per year. Interesting, huh? Look, you'd think there's a major change, but no. Going from 6 months to 12 months, you end up with 13 cycles per year, which is it's quite interesting. Okay. Okay. Optimum interval selection. The author considers that the winner in the above calculations is that which provides the highest balance toward achieving PM access to the machine, standby active testability, where you were able to test it, does it work or not, greatest reduction of start-stop cycles on main and standby machinery. These are the ones you're trying to eliminate or meet. You want to meet all these users, all these demands. This leaves the 6-month start-stop model as the ideal. According to my article, this is the ideal. 6 months start-stop as a switchover. However, the machine that is not operated is just turned on for once a month for a short period of time, could be half an hour, just to test everything and bring it back down. Okay? Good. And then it goes on to what if you have an ABC machine, so 3 machines running, same calculations are applied. ABC, and then AB, if you have 4, also, it shows how it's applied. So, examples of the short stop interval, no, that's already, you can read that on your own. So, philosophy. The above calculations attempt to capture the relationship between time interval and operating and shutdown modes as compared to frequency of damaging cycles. The author considers that the winner in these calculations is that which provides the highest balance. Okay, this leaves the 6-month model as the ideal. Reduction of machine stress monthly test starting in the 6-month mode. The yearly number of starts is the same as for 1 monthly switchover interval. However, the operating temperatures of critical parts don't reach the higher temperatures achieved under long-term operation. In addition, the monthly test startup of recip engines or steam or gas turbine-driven machines, the shaft speed does not have to reach 100%. So machines which are variable speed, they don't have to reach 100%. What's an example? Diesel generator. Diesel generator, you don't have to go to full rated speed. You can go to half speed. Because once you've proven half speed, it's enough. So if you want, of course, you can bring it up to full speed. But during this 1 monthly start-stop test, you're only checking basics, you're at minimum loading, and you're just testing it to make sure it's available, and it's lubricating the components. Important, remember, just the air we have around us has salts and it has moisture. They corrode parts. So we have to get oil to them. Okay, and it goes on. You can read these details later. So here we discuss procedures for pumps, motors, pumps, steam turbines. Maintain operating blowers or pumps designated as a main machine. For A and B configuration, standby compressor or pump is only started once monthly for 1 hour maximum recycle if it's a pump. So you start it once monthly for 1 hour on recycle. You don't put it into service. You just let it turn around by itself. If it's an air compressor, same thing. You let it blow off into the air. For half an hour, everything's fine, shut it down. But you're not putting it online. And same for reciprocating. And the article is self-explanatory. Okay. Are we done? Is the time limit reached? Okay. Great. Yeah. Thank you. Thank you very much, gentlemen.